Okay, guys, so welcome to the Robotics and Artificial Intelligence meetup number 55. And in today's session, we'll talk about how the startup Sewts is enabling robots to handle deformable materials. So, we'll have with us the co founder of Sewts, Till Rickard, who will be sharing about Sewts and what are the products that Sewts has built and what are the areas and applications of robotics that Suits is currently involved in. The agenda would be after this very short introductory presentation from my side, I'll just hand it over to Till, who will do the topic presentation, which will be followed by a Q&A session. You could also ask questions while Till is presenting, so it would be more or less an interactive session. And after that, we could have an introductions and casual networking. So the last part is more optional. If you have the time, you could stay and we could just generally talk about what your background is in robotics and what your interests are and so on. So what are we doing here? So we are an active learning group of robotics and AI enthusiasts, and in the past several months I have been inviting guests from lots of different research institutes and companies to share their experience and talk about several aspects of robotics and artificial intelligence. And this is a new format that we have adopted. Before that, we had a theme based system where we would have a monthly theme. For example, for one of the sessions, we had humanoid robots as the theme, and we had several sessions related to that. Everyone can actually participate in the Discord server and also on the meetups. You can take up several roles, like you could volunteer to present your project you could check the meetup volunteer channel, or you could share your research papers in the paper reading volunteer channel. And one quick thing to point out is that the meetings would be recorded and shared online. So if anyone has any issues regarding that, you could just reach out to me at the end. Maybe you want your introduction to be edited out, and I could manage that as well. There are a bunch of different roles which you can check also in the assign roles channel, and all of the resources are shared on the website thebuildingculture.com. So the presentation and all additional resources related to today's session would be shared there. So let's start now. I'm excited about today's session. So over to you, Till.
Okay, thanks, Chandandeep. Hello from my side, guys. My name is Till. As Chandandeep introduced me shortly, I'm one of the co-founders of Sewts. And first of all, I will share my screen and hope you can all see it then. You guys should be able to see a presentation now.
Yeah, your presentation is visible.
Okay, nice. So yeah, thanks Chandandeep for the introducing words. As you already said, everyone feel free to just hop in with questions at any time. So the presentation can be interactive. I don't want to keep it too long to leave enough room for discussions and questions. Yeah, and I'm just gonna introduce Sewts a little bit, the startup that I founded with two of my friends after studying. And I'm gonna talk a little bit about the challenges that we're facing, how we do it, which use cases we're tackling, and share also some videos of our latest results. Yeah, so I took the title. I gave the title "How Sewts Enables Robots to Handle Deformable Materials," and I'm very happy to speak about this in the Building Culture meetup here. And I want to start this with a question. It's here on the slide. Technology masters traveling into space and 3D printing of vital organs, but it is not capable of teaching robots to sew your t-shirt yet. Why is that? So as you can see, what we're doing is related to textiles. You have the example of a t-shirt here. And we're focusing here at Sewts at all kinds of industrial processes in which deformable materials like t-shirts or towels are processed, handled, manufactured, everything you can think of. And it's just a very interesting question why we as humans have delivered so many technological advancements as of now, but still such a task like sewing a t-shirt or sewing a towel, whatever, is still done by humans. And it seems kind of ridiculous that we travel to space, but we still need very much human labor to produce our clothing. And this is a question which my co-founders and me started to think about during our studies at Technological University of Munich 3 years ago. And we thought, okay, what could we do about this? And first of all, I think we need to talk a little bit about the challenge here. So I've already introduced you guys to the field of deformable objects and the robotic handling of deformable objects. And what is the challenge here? So deformable objects and deformable materials, they have very, very complex material characteristics, meaning as soon as you touch them, like your shirt, your t-shirt, your towel, as soon as you touch it, it will deform. And most of the deformation happens unpredictably. And this is very hard then for automation systems in general and for robots more specifically to deal with. And those complex material characteristics, they require enhanced handling abilities, which we as humans already provide. So you could think of cognition intelligence, sophisticated vision technology, the process knowledge on how to deal with this uncertainty, and also the mechanical sensitivity in your fingers. And current automation systems, current grippers, current robots do not provide these sophisticated abilities. And this is why we have a lack of adequate automation solutions in these industries. And we have a gap of automation here. And yeah, that answers the question that I posed on the first slide. The reason why robots can't sew or at least wash your t-shirt today is because those complex manufacturing or assembly tasks require very, very high skilled abilities. And currently humans are unbeatable in the combination of perception, three-dimensional and visual awareness, of course, experience, and dexterity. Imagine you show a friend or a kid of yours how to fold a towel together. A human just does this 2 or 3 times, and after that, a human can basically fold every single towel in the world because our human brain works in such amazing ways. But this is not the case for robots. If you, let's say, teach a robot how to fold a towel one time with this specific towel, and you put another towel there, it's most likely to fail because a robot in the end is, let's say, very focused then on the task that you taught it and that you programmed it for. And this is exactly the reason why the handling of deformable objects is so difficult for robots, because textiles are never the same. The appearance of a textile, even if it's the exact same textile, it will change from time to time. It will look different. It also changes the appearance over time, over its lifetime. So it might change the color a little bit. It might change the the surface a little bit, it might change its weight. And this is all kinds of things that, let's say, automation systems cannot really cope with. And what do we do about it? We at Sewts, we develop perception software for robots, and we design processes to assist them. Because, of course, it's a dream that you have, let's say, a robot with some kind of general intelligence that can cope with everything and can do anything. But in reality, you have to find a good mix. So you have to equip your robotic system with enough intelligence to deal with this uncertainty. And you have to provide the automation system and the robot with, let's say, a tailored process to assist it. Because, of course, we have lots of progression and advancements in gripping technology, for example, but we are not there yet that we can replicate, for example, the human hand. It's not possible yet. So you have to find a good trade-off between adding intelligence to your system, but also do not forget to design a good process so that the system is, let's say, from a mechanical point of view, even capable of doing the task that you wanted to do. So let's say, to phrase it more on a higher level, you could say you always need to bring together software and hardware in the end. And we at Sewts, we focus on exactly that. So we at our core technology, what we call our robotic brain in a box, we develop artificial intelligence. So most of the times we use machine learning algorithms, deep neural networks for that, and we develop perception software, you could say. So we take a use case and we train, for example, a computer vision system to provide our automation system in the end with the necessary information, handling strategy, grasping points to handle deformable objects. So at the core of our technology, we develop perception software with machine learning algorithms. And we add to that the process know-how. So we look at the process that we want to automate, and we design a process that is suited for an industrial robot together with an intelligent cognition software. Because like I said, you have to think about software and hardware in the end. So the process design is really, really important in the end. So we have our, let's stick to the naming, our robotic brain in a box, which we provide with some sensor inputs like cameras, force sensors, LiDAR sensors, whatever. And in the end, this brain outputs some actions to a robot or to multiple robots. And in the end, we built an automation system around, let's say, this structure. And one clue how we do this, and one solution that we have here is that we use simulations of textiles to train our AI models. Because probably all of you guys know it, if you want to train powerful machine learning models, you need a lot of data. And if your data, let's say, is requiring you to have data of textiles and of moving textiles, it can be a real pain in the ass to get a data set together to train something. So what we do is we use synthetic training data, which we create ourselves by using FEM, finite elements method computer simulations, where we then can produce tons of already labeled data to train our machine learning models. And I will give some examples of how this looks later. Let's just quickly talk about what use cases are possible with this. So we're talking basically about everything where deformable objects are involved. It could be laundry and wash services. It could be the handling of returns in e-commerce. Of course, our big vision is fashion and workwear. So we're suits. We're trying to sew a suitable suit in the end by robots. This is where our name comes from. This is our big vision. But you could also think about, let's say, use cases where there are no textiles, but other deformable objects, for example, foils or cable routing in electronics and automotive industry, also food and meat processing, rubber parts, wrapping, whatever. So all of these industries have the same problems with deformable materials, and this is why they're very labor intensive. And this is all the industries we envision one day can be automated with our technology. Why are we doing this now? There are a couple of drivers that drive us. One of course is that there's now the processing power available. So I don't know, 10 or 20 years ago, you could only dream of what computers can do now, and it's really important if you want to train on huge data sets, if you want to have a big machine learning models, you need the power, but I think all of you guys know that. The same is for robotics hardware. So if you look at industrial robots, so 6-axis robots, for example, you can see a 10% price drop per year averaged over the last 10 years, meaning that these robots start to get a commodity, and you can build automation systems at much more competitive pricing compared to 10 years ago. And I mean, we don't want to talk about Corona too much here, but Corona has shown some crucial weaknesses of the global supply chains. If you just think about facial masks or everything that has been missing in supermarkets for some time. And the world is demanding for more resilient supply chains. And one way to do this is, of course, to relocate some of the production sites closer again to the actual markets. And if you want to do this, depends on the country, but if you want to do this, for example, in Europe, you will need automation technology to do that. And last but not least is, of course, there's a rising consumer demand for local production, mass customization, and sustainability. So getting to a greener planet by reducing transportation routes and by reducing waste. If you think about big, say, fashion companies, they produce much more T-shirts, for example, than they need, just to have them everywhere at the same time, readily available. And if, let's say, they change to a new line, to a new fashion line, they just all those T-shirts go to waste. So these problems you can solve with just-in-time production, just-in-time delivery, but in the end you need automation for this. So this for a little introduction of everything. Now I want to get a little bit more into the tech side, give some more specific examples of what we're doing. So I already said that we're using simulations for training our models. On the left side, you can see a typical example of such an FEM simulation. These simulations are normally used to simulate technical textiles. For example, if you think about carbon reinforced plastics, which consist of, let's say, a technical textile, a carbon weave, whatever, which is then infiltrated with a matrix. There's a lot of simulation going on there to optimize those materials. Of course, we don't need such let's say, exact simulations. You can see on the left side that every single fiber basically is simulated. We do not need that. Let's stick to the example of a towel. So we adapted those simulations for our needs, and we used them. For example, here you can see a towel to simulate towels. And after that, we apply a photorealistic rendering and generate tons of synthetic training data for our training. And of course, if you simulate a textile, you know what you simulated where, which means you get the labels for free. So you know where the different features of your textile are, and you don't need a human worker anymore to label this data for you, meaning your simulated data is already labeled for you and you can use it for training. And this is how we save over 5 minutes per image. And if you think about big data sets with thousands or even tens and hundreds of thousands of images, you save a lot of time. And this allows us in the end to verticalize quicker than normally into different use cases, for example, with the computer vision system. So on the right side, it's maybe a little bit small, but you can see that those are real towels, and a machine learning model predicted where the seams of the towels are, and this machine learning model was trained on synthetic data. So you can also imagine if you want to build an automation system for t-shirt processing or t-shirt manufacturing, and you need to extract some visual features of a t-shirt, you can easily generate simulated and synthetic data of t-shirts, which is already labeled for your purposes, and you can use it for training. I just want to give you guys an example how such a simulation looks. So here you see basically a towel hanging in the air, and what we do is we let it fall to the ground, and in the end basically it's a crash simulation of a towel. Here, for your convenience, we have already applied the rendering. Of course, if you simulate such a thing, you would not see the rendering, but we made a little video for you guys where you can see how this is looking. And yeah, I've come back to the example of a towel now quite some time, and you might be interested and might be wondering, okay, why is this guy talking about towels so much? So if you remember the use cases I showed you, there was also laundry and washing services as one use case. And we're definitely, let's say, not a laundry startup, but it's one of the use cases. And we thought, okay, it's a nice use case to start off with, to go to industrial laundries and automate how towels are processed there. Because right now, in industrial laundries, it's quite automated, but there are lots of steps in between automation systems where humans need to handle and place towels, because after each automation step, for example, imagine the washing of a towel and the drying, and the towel gets out of the dryer, it is completely deformed and it's in an uncertain and unknown state. So every towel looks differently, and after that, towels are supposed to be folded together. But to fold a towel, there are already machines, but those machines need the towel in a deterministic and always the same appearance. So they need the towel flattened out and not crumpled. And this is what humans are currently doing. It sounds really easy, but it's a highly complex task. And we started off to develop a prototype for this, which I want to show you here. So basically here you can see what the task is. There's a towel in an undefined state. It's crumpled. It's lying on the table. And the goal of the system is to place the towel without any folds and in a flat way onto the surface. And this is what's going on here. So there's a vision system extracting features of the towel and telling the robots where to grasp the towel. And in the end, the robots do that. And what we also did is we developed this mechanism on how to slide alongside the seam of a towel to open it. And what you can basically see here is exactly what human workers are doing every day in every industrial laundry of the world. And there are a lot of industrial laundries in the world because we humans produce a lot of dirty laundry. And it's for a human a quite simple task. For a robotic system, this is really, really challenging. And this was just a prototype. I would like to share with you guys a more industrialized version of the system now. So what you can see here is basically how the system evolved. You see now a really big industrial robots and safety technology, everything. I'm just going to play it for you. So we use two computer vision systems here. One is located over the bin of towels here. And here we are basically separating single towels out of this bin of towels, placing them on a conveyor. There's already some magic happening here because the way we grasp the towels here and place them here has the goal of exposing graspable areas of the towel for the second robot, which is not that easy. The second robot is also connected with one of our computer vision systems, which extracts, in this case, the seam features here and analyzes the towel's topology and gives commands where to grasp the towel. And in the end, the towel is handed over to what we call, in the end, our sliding unit here, where the towel is then opened up and placed on the folding machine. And this is now an example of how much sophisticated tech you need to replace one human worker who is doing the simple task of placing towels flat onto a folding machine. And I think this is a really good, let's say, gives you a good grasp of how complex all of these tasks are. Because in the end, for a human, this is really easy. For automation system, this is not. And just to replace this one human who opens up towels all day long, you need such a big system. And now imagine what you need to sew a t-shirt, for example. And yeah, this is our big vision. We want to do this one day. We want to do our part of, let's say, solving the global problems that I have described earlier. And one day we want to sew a suitable suit, fully automated, fully mass customized. And yeah, thank you very much, guys, for your interest in this topic and listening to my short presentation. If you're interested in how this is going on and how it develops in the future, make sure to follow us on LinkedIn, where we always share our, let's say, latest videos and latest breakthroughs. And yeah, thank you very much. And I'm very happy if you guys have any questions to start a discussion with you now. Thank you.
Yeah, thanks a lot, Till. That was a really wonderful presentation, and I think it gives a really good picture of how difficult deformable object manipulation is. And I'm also excited about the new use cases that might come in the future, and how you're going to tackle more challenging problems in robot manipulation. So let's hear from. Let's hear if anyone has any questions regarding the presentation.
Yeah, I got one question.
Yeah, go ahead.
You can set up my camera.
Yeah, we can see you.
So you didn't build the robots yourself, right? So the videos you have
No.
shown, you bought them. Okay, because I was wondering, like when I'm thinking about doing a startup company, I need at least a couple €1,000 to start off with, I don't know, buying robots, building an infrastructure, renting offices, a workshop. And I thought, how did you overcome those first obstacles when you're small and you see all the industries having a lot of money and you just don't? How did you do that?
That's a very good question. And at the time, we were 3 poor students, so we definitely could not afford even one of those robots. So what we did, and which is a very good situation here in Germany and especially in Munich, you have at the Technical University of Munich a lot of support programs for young founders. Meaning it's one initiative is called the Unternehmertum, where you can basically pitch your idea, and then you get some support. At this stage, probably even if it's bad or if it's good, it doesn't matter. You get some support on how to figure out yourself whether it's good or bad, and they also then help you to get public, for example, public support and public funding for your project. So what we did is there's a program by the German state which is called Exist, which is basically a scholarship which provides up to 3 founders with their cost of living in the end, and you get 30,000 euros for prototyping. To get this, you have to hand in a business plan and basically convince them that what you're trying to do will provide some benefits to the world, and of course in this case to Germany, especially because they're paying for it. And yeah, this is how we could afford our first robot with this 30,000 euros, and we were able to build this first prototype with the 2 robots that you saw. So we bought 1 robot, and the second robot was financed through a different program by Unternehmertum, and basically this is how we were provided with the resources to build this first demonstrator. And of course then if you saw the development from this demonstrator to an industrialized version of the system, to do this, you need a team of engineers. You need the tech, because those big industrial robots, they're like more in the range of 50 to 60K per robot. You need all the surroundings, the peripherals. So you would easily need, let's say, to get it to that stage, around 1 million euros. And to do this, how we did it is we basically went to lots of startup fairs, met potential investors, and in the end of 2019, we were able to convince some investors of our technology, and did our pre-seed financing round with some business angels, and got the first external money in, and by now we have done a second funding round, the seed funding round, with new investors coming in, and basically, yeah, this was for us the only way to do this, because I mean, it's not. I don't want to say that app development is not hard or anything, but you can develop an app without a lot of money if you do it yourself. But if you want to build, let's say, a system like this, where also lots of hardware is involved, you need the money. And for us, the only possibility was to convince investors and get external funding.
So you probably sold most of your stakes, right, to investors?
I cannot give you any numbers here because those numbers are confidential. Sure. But let's say if you sell most of your stakes, you lose the fun in the game. Yeah. So right now, let's say in the USA, it's even more common, I guess. But the VC and startup ecosystem is getting better in Europe as well. And if, let's say, you can convince with your idea and with your team, especially your team is important, and of course you have some luck, you can also get in external money without selling too much of your company.
Okay, thank you. It was very, very interesting.
Yeah.
Very good
Thanks.
insights.
Thanks still, and thanks for the question. So does anyone have any other question as well? It could also be related to deformable objects or one of the slides that was shared. Okay. Looks like not. Maybe then you could just um, introduce yourselves very shortly, and any general remarks, maybe what you learned today, about deformable objects or something. So let's start with Goblin. I'm sure that's not your real name, but we could start with you.
Yeah, actually, I'm a student in MIT WPO, Pune. Uh, I'm a robotics engineer in third year. I'm pursuing my engineering as of right now. This is my first day and first session on this server.
Oh, that's nice.
The session was very nice. It was a bit, uh, how can I say this? A bit too much technical, as much up till the experience that I've had up till now. But I'll surely catch up as soon as I can.
Yeah, I mean, since this topic is also new to you, probably then that makes sense that it was a bit too much to catch up with. But you could always check the recordings at the end, right? And
Yeah.
hopefully you could at least appreciate the complexity of deformable object manipulation and the things that are going on in robotics.
Yeah, I had no clue about this topic. So it was a very interesting and a topic that I did not know existed. So I hope to get into this and look into this.
Okay, perfect. Yeah, yeah. Thanks and welcome to the server.
Okay, thank you.
Yeah. Okay, and. So, Milano, I mean, you already asked a question as well. Maybe you could also introduce yourself. You've been here before, but just general where you're from and what you're involved in, and so on.
Yes, for sure. So I'm also a student at Technical University of Munich, as well as Till was a couple of years ago. I'm doing my master thesis about soft robotics and visual servoing. And yeah, I'm excited to hear about people's stories, since I'm also probably uh, I'm finishing my studies, so I will start working in the free, how do you call it, free market, and I'm curious. I'm curious to hear people's stories, and I'm super excited to have joined you.
Yeah, yeah. You're welcome. What's your real name again?
My what?
Your real name.
My real name is Milan.
Okay,
So
okay, okay. Perfect. Yeah, you never know because on Discord people use
yeah,
nicknames and so on, right? So yeah,
yeah.
so let's go to Juan Diego. So here again with your introduction.
Hello, everyone. Can you hear me?
Yeah, we can hear you, but
Yes.
the audio is a bit too low. Maybe let me see. Yeah, it's fine. Go ahead.
Okay. Anyway, well, my name is Juan Diego. Yeah, I'm a mechanical engineer. I am doing my master's in robotics, and I want to ask Till about the simulations about these soft materials. Uh, I want to know. I mean, you show us different kind of applications, such as maybe food and these kind of things. And I wanted to ask you if there is already some data or information about how to simulate different things besides tissues and these kind of things that you showed us. And 'cause the simulation really got me and it was really really cool actually. So I wanted to ask you about that.
Mm-hmm. So I didn't get everything of the question, but I heard that it was about the simulations, and so I'm just going to talk a little bit about that.
I want to ask you, I'm sorry, if you can simulate those kind of things that you show us, like food, plastic, and those other things besides you know, uh, the simulation that you show us.
So currently, we're just focusing on textile simulations, meaning, let's say if we wanted to simulate, you saw a towel in the example, it would be, let's say, relatively easy for us to do the same thing with a t-shirt or with a bed sheet or whatever with the jeans, because how we do it is basically, of course, you have to define the geometry of the thing. For a towel, it's really easy because it's just, let's say, a rectangle. For a t-shirt, it's a little bit more complicated, but still not really difficult. The second thing is that you have to model the material itself. So what you have to basically either estimate some material characteristics, or you have to really measure them. There are some special tests to deliver, I don't know, the bending stiffness of a material, for example. You can do that, and if you either measure or estimate those parameters, you can put them together to a material card for that material, and that you basically put into the simulation. So you have your geometry, you have your material card with all the properties of the material, and then you need to think about your simulation environment. So what you saw, what we did with the towel was basically we pinched it at a random point, lifted it up into the air. This is where the video started, and then let it fall to the ground. And what we did there was to simulate all of the air resistance spreading out the towel, and then it was basically a crash simulation to simulate how the towel crashes on the surface. This is how we simulated the towel, and basically this we can all reproduce with different kinds of textiles. If we think about, for example, you asked about food now, simulating food. The step going from towels to food is a little bit bigger than going from towels to t-shirts. Still, the pipeline stays basically the same. But we have never done this, to be clear. The second step is then the rendering. So first, you simulate how the material behaves and how the material deforms, and after that, depending on what you need, you render a surface onto the material, basically. The video that we showed you, there we rendered the surface basically on every time step of the falling towel. If you just need, let's say, an image of how the towel looks after it has fallen on the surface, you would just render the last step of the simulation, because it's also computationally intensive. But what we did for the video, we rendered basically every single step of the simulation and put all the images behind each other to have a video. And of course, same thing, rendering textile surfaces and rendering, for example, food surfaces is of course different, and you have different challenges there. So there's also the same, the pipeline stays the same, but of course, if we want to simulate, I don't know, how a leaf of lettuce is falling down to the ground, we would have to investigate a little bit how do we do the rendering for, of course, also.
Yeah, thanks. Still, it was very detailed explanation. So, Juan, you're satisfied with the answer, right? Your question is answered.
Thank you
Okay.
so much.
Okay. Yeah. Thanks. And so let's go to Pradeep.
Hello,
Hi.
hello.
Hello.
Yeah, hi. Thanks, Till and Chandandeep, for this amazing session. First, so I am Pradeep. I am actually a robotics student at RVTH. I joined this winter semester, and I found this channel through LinkedIn. And this is one of my first sessions, and I like the sessions. Thank you. I am just starting into robotics, and I find this helpful.
Okay. Great. So you just started at RWTH Aachen with.
Yeah. I just started. Yeah.
Okay. 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 So it's your first semester.
Yeah. And I'm new to robotics. I worked in automobile and I'm new to robotics and this channel is actually helping me to learn all the robotics fields and use cases. And thanks still especially today for the amazing session.
No worries. Glad you came to listen.
Okay.
Yeah, thank you.
Perfect. Do you
Thank
also
you.
have any questions for Till, or just that's it?
Yeah, I think that's it for today. Thank
Okay.
you.
Okay. Thanks, Pradeep. So let's go to Sachin now.
Sorry, I maybe got another question.
Yeah. Yeah. Go ahead.
It's connected to Juan's question before. I'm sorry if I missed something, but you also you also mentioned before that you did these simulations for labeling the dataset easier, right?
Mm-hmm.
I just cannot imagine right now, like, what is the label? I mean, is it like folded, unfolded, or what is the label exactly?
Yeah, good question. I can explain this. So maybe we just stick to an example of a towel. So you saw a system that is handling the towels, and for some of the process steps, for example, the first one where we pick a towel out of the big pile of towels, we're very interested in picking only a single towel. And one way to do this is to identify where is the seam of the towel. So basically, a seam would be like at my T-shirt. This would be the seam here, and this is not the seam. Yeah, towels have a similar thing. So one step of our pipeline is to train a computer vision system to identify seams like this. And in this example that you saw, we do it with a towel. So when you want to train the machine learning model to identify those seams, and you do this with real data, you basically take images of real towels, and then you have a human label the seams for you. You could do this as easily as with paint, if you would like to, or you use a dedicated labeling tool for that, which is basically then sophisticated paint. But it's, let's say, very annoying work, because to do this accurately, you have to label every single pixel of your feature, and then you provide the machine learning model with your data set and these labels, and hopefully it learns how to extract the labeled areas, which are the features you want, in this case the seams. And if you simulate that, so if you simulate your textile or your towel, you set up the simulation in a way where you can later on automatically distinguish between, let's say, the seam part and the not seam part. You can, for example, do this by using a different mesh for this part and that part, which you then stick together. But in this way, you can always know where are all the seams that I simulated in the specific simulation, meaning that you can quite easily generate the labels that normally humans would create. You can auto-generate them. This is the magic of simulated training data in the end, because you save all the human labeling effort, and you get the labels basically for free in the end. Did that answer the question a little bit?
Yeah, so it's if I understood correctly, it's the positioning of the seams, right? That's the
Yes.
label. Right? So you
In that
just
case,
marked
that's the label.
yeah, so you just marked it in the, let's say, construction or whatever file you use for a simulation, then it was visible beforehand, right? For the robot.
Exactly. So when you set up your simulation, you basically, let's say, normally when you set it up, you start by constructing a flat towel in simulation, and you you let's say assign a property to every point of the simulation. And one of those properties could be, okay, this point of the towel is a seam, and another point is the terry. And you do this basically with every point, so you know, okay, this is all my terry, this is all my seam. Then you simulate it, and even after everything has deformed in simulation, you still know which points of the towel are seam and which are terry, and you can use that information to basically assign a different color to the seams, which you can then use as labels for the machine learning.
Yeah. But still, when the robot views the towel, he doesn't have this information, but only the visual input he gets, right?
Yes.
Would have been not would have been. Then I'm wondering, just curious, isn't it that possible to, let's say, take a towel and we mark the seams with a red pen, like this? Wouldn't it have been also been possible to do that, like without
Yes.
simulations then?
Yes. You mean for training the machine learning model?
Yeah.
Yeah. Very good idea. We also all did that. So it's of course you have some challenges there. But it's definitely, it is possible to do it, and then you can basically generate real training data with real, I mean with real towels, and kind of automate the labeling work. And this is an approach we've already tried, and it works okayish. So
Okay.
you have some problems that depending on the color you use, you cannot be really exact, whatever, with this kind of stuff. And also you have to make sure that you don't change the appearance of the textile too much, because if then all of your towels have red seams, and normally the towels that you process in the end in the system have white seams, you get a problem. But it's possible, yes.
Yeah. Okay. Thanks.
All right.
Yeah, thanks, man. That was a good question. Yeah. So moving back to Sachin.
Sorry, I lost you. Can you, what I'm supposed to do?
So yeah, we are just having a small introduction session, and if you have any questions for Till, basically.
Okay. Hi everyone. My name is Sachin, and it's really nice to meet you all. So actually, I was not able to attend.
Oh, you
Like,
joined late, right?
yeah, like there was some work
Okay, okay.
around, so I don't have any questions.
Okay, sure, no worries. Yeah, you can always check the recording later. So yeah,
Okay.
let's.
Thank you.
Thanks, Sachin. Uh, moving to Shaurya.
Yes. Hi everybody. So I am undergraduate at MIT WPU Pune. So I am currently doing my final year project there. So I am doing my final year project in soft robotics. So I don't have a question for this session. Like the deformable objects were a new topic for me also, like that.
Okay, perfect. Yeah,
Uh,
thanks, Shaurya.
but But I have a question for Milano. So what is he doing in soft robotics?
Yeah, for sure. So I'm writing, I got accepted at the DLR for a master thesis about tendon-driven soft robots. So it's basically the neck of one robot, which is tendon-driven. So you can imagine it like two platforms, and they're connected with tendons. So
Okay.
one platform is like our neck, able to rotate and to move around, and we want to control this neck with a camera on it. So that's the eyes. You have two cameras,
Yes, yes, yes.
and with this camera, you want, for example, follow a car. So if you see a car, let's say it's a fast Lamborghini, you will probably follow it with your head. You will look at it, and we want to imitate this. So we want to see objects and control the neck based on visual signals. So that's called visual servoing, and that's what I'm doing. Yeah.
Okay. So for simulation things, which kind of software do you use?
So I'm using MATLAB, but I could have also used Python or C++.
So for that designing simulation.
No, we're not doing simulations actually. We're using real time, so real life data input.
Okay, okay, okay. Yeah, nice.
No problem.
Okay. Yeah. Thanks, guys. So yeah, maybe we can just have one last question before we wind off. If anyone has anything to ask. Okay, I think you guys asked lots of questions already, so should be fine. So we can wind off today's session. So thanks a lot, Till, for taking out time for this session. I think it was really wonderful. You explained the whole pipeline of how the towel is being picked and fed to a folding machine, and also different use cases of deformable objects and how it is a challenging problem and so on, and how a synthetic data set is actually so important for machine learning scenarios. So so yeah, thanks a lot for joining today's session, and hopefully I'll invite you again in the future with more use cases and so on.
Of course, was happy to be here.
Sure. So thank you, and have a nice Sunday.
Right. Thank you, guys. Bye bye.
Bye.
Thank you.
Yeah.
Thank you.
Bye.
Bye.